Okay, so let's draw the shear force and bending moment diagram for this problem. It's 431. The interesting thing here is that you'll notice that there's a hinge right in the middle. Now, what do we know about a hinge in terms of shear force and bending moment? There's going to be shear transferred, but is there going to be moment transferred? No. So you need to make sure that your moment diagram hits 0 there. What about the moment at this pin connection? Also 0. And all the way out here at this other pin, you should have 0. Now, this section here, this vertical section, really is a weightless link. So we know that the reaction force is going to be collinear with the element. So it's just going to be one reaction. Okay? So this problem is going to require you initially to do some statics. So I'm going to come over here and draw my two free body diagrams. So I'll separate it into this piece, which will be piece AB. So I'll have a reaction at A. And it is a pin, so I'll say there's an X reaction. And then I'm going to separate it here at B, and I'll also assume reactions Bx and By. Let me go ahead and label this up here. This would be free body diagram for AB. Now on that particular section of the beam, what's the load? Well, it's a distributed load of 5 kilonewtons per meter over 2 meters. Let me go ahead and put that in there. So I'll get a concentrated equivalent force of 10 kilonewtons. And it should act in the middle, so that would be 1 meter. And then my free body diagram for section B, C, and D will look something like this. So I'll have my Bx and By will be equal and opposite. Then I'll come to my reaction at C. I'll assume that's up. That's a roller, Cy. And then I'll come out here to my pin at D, and again I'll assume dy and dx. Now the concentrated equivalent force on this element, again it's uniform distributed, 5 kilonewtons per meter times 2 meters, it's the same. And then we already know these dimensions. And it's the same as before. So I'll go ahead and pencil all those in. So what to do with this one's going to require us to do a little work to start with. So looking at these two, which one should I do first? If you first notice that all the x components, right? If I sum forces in the x direction, it says that ax plus bx has to be equal to 0. Bx plus dx has to be equal to 0, but there's really no forces in there. So the x components we can kind of ignore. So if you look at now at remaining unknowns, AB has 2 and BCD has 3. So we'll start with this one first. And I'll just start by summing moments about B. You can sum moments about A if you like. So summing moments about B, I have the moment created by the 10 kilonewton force, which is positive moment, the moment arm of 1 meter. And then I have AY creating negative moment with a moment arm of 2 meters. It's not hard to see that AY is equal to 5 kilonewtons. And then if you sum forces in the y direction, you have AY acting up, BY is up, and then my 10 kilonewton force is down. And again, it shouldn't be a big surprise that BY is also kilonewtons. If you look at this section, it's really just two forces. The load's right in the middle. It takes half on each side. So that set goes to this free body. Now we'll do the next one. I already know By, so I'll sum moments at D. Again, you could sum moments at C if you like. The results should be the same. So if I sum moments about D, I have my 10 kilonewton force with the moment arm of 1 meter, and that creates positive moment. I have By, which I found was positive, so it's acting down here. That also creates positive. So I'll just say By times 2 meters. Then Cy creates negative bending moment about D with a moment arm of 1. So if you put your 5 in here, you get 10. 10 plus 10 is 20, divided by 1. Know what it sounds like to you? What's Cy? It should be, did I do that right? Yep. 10 times 1 is 10. 5 times 2 is 10, so that's 20. So it should look like Cy is 20. And then finally we can get the rest, or actually Dy. So we can sum forces in the y direction. So I've got, I'll start from the left side. So By is acting down. Cy is up. Dy is up. And my 10 kilonewton force is down. So we know By is 5, Cy is 20, so that's 15. 15 minus 10 is 5, so it looks like Dy is minus 5. Does that seem reasonable? Makes kind of sense to me. If you look at this element, imagine Cy is a pivot and it's got to be balanced. So if By is down 5, it makes sense that Dy would also be down negative 5. So we finally get all of our pieces. So let's see if I can squeeze in the moment diagram over here. So I'll start with a bracket that says the outline. I know something important is going to happen here, so I'll include that. And also in shear, I know something important is going to happen there. It's a support. So let's go ahead and see if we can draw the shear diagram with units in kilonewtons. And I'll come down here and remind you that, remember, the change in shear is the area under the load curve. And of course, the slope of the shear diagram is equal to the load. So let's not forget our fundamentals for constructing the diagram. So what is the shear at A? Well, 5, and it's up, so up on the left side is positive shear. So we're going to start at 5. So the change in shear is the area in the load curve. What's the area between A and, what is that, C? What is this area? Well, it's base 3 times height 15. So that's negative 15. So 5 minus 15 brings you to 10. Okay? And what's the slope of the shear diagram? It's equal to the load. What's the load? Constant and negative. Actually, it's negative 5. So I can draw that like so.
So that pivot doesn't break the connection?
No, because what do we find the force at By to be? 5, right? And what kind of shear is that? Positive or negative? Negative. And you'll notice here we have negative 5.
So
I'll just go ahead and pencil that in so you can see that. That's negative 5 right there. Of course, this value is negative 10. So it matches. It also points out we have a new point to consider. That point.
Where is,
because the shear is 0.
now why is that -10?
Well, we followed our rules. The change in shear is the area under the load curve, and we're going from A to B. Because we know at B what's going to happen. An external reaction is going to cause a change in shear.
So 3 times 5 is 15.
Right.
Gotcha.
So following that line, what is CY? CY is 20. So -10 plus 20 brings us to +10. Right? And now what's the change in shear over this length? Area under the curve, 5 times 1 is 5, and it's negative. So that's going to bring us back to 5. And the slope? Well, the slope is equal to the load. The load is constant and negative. So there's your shear diagram. Now, does it match here? This says you have a positive shear of 5. So go out here and look at your reaction. What do we find dy to be? -5, which is down, and down on the right side is positive shear. So it matches. Anybody get that, by the way? One couple people? Okay, cool. Yeah, sorry.
Is it wrong if you just keep the two parts separated and do a shearing moment for each one?
No. I think if you assembled them, you'd see the same composite diagram. Now we can go ahead and figure out this piece the way I've talked about before. Is if you extend this line up, then, and I'm trying to find this distance, I'll call it, say, x1, then go back to our diagram here. The change in shear that we're looking for is what? Well, we're starting at 5 and we're going to 0, so that change is -5. The area under the load curve in this same segment is this area. And what is that area? What's the area of a rectangle? Base is x1 times height, which is 5. So that should be -5 times x1. Of course, if you set these two equal, what do you get? 5 is equal to 5x1, so x1 is equal to 1. Another way to get that would be similar triangles. You can see these two triangles are similar. They have the same slope. They have the same height. So this should be the same distance for each. So 2x1 should be equal to 2. x1 is 1.
So just because the dy's force is -5 doesn't mean that's where the shear will be at the end of the diagram.
That is the shear at D, yeah.
Is
It's caused because this thing here is pushing up and shearing it.
okay, so why is it +5?
Well, actually, it's positive shear, which actually means the force is down.
Okay.
It's pulling down on it.
Gotcha, okay.
I said up, but you're right, it's down. All right, so let's do the moment diagram now. So I'll put my positive x in moment, and these will have units of kilonewton meters. Now, there's some things that we do know. We know the moment here should be 0. We know the moment here should be 0. What else? I guess the moment here should be 0. Now, what's unusual is this point right here. We usually don't have information about the moment out in the middle of the beam, but this is unique because it's a hinge. So let's use our second set of relationships, that the change in moment is equal to the area under the shear diagram. And, of course, the slope of the moment is equal to the shear. So this is the next set that we'll use. So starting here and applying this relationship, the change in moment is the area of the shear diagram. Well, what's the area of the shear diagram here? What's a triangle? 1/2 base times height, right? And that's a positive area. Remember, x1 is 1, so that's just 2.5, right? So we go up to 2.5. Now what's the slope? It's equal to the shear. The shear starts off at what value? A positive value, and slowly decreases to 0. So those should tell you how your quadratic curve is shaped. Now we go over the next segment, which is here. And what do we get? Well, the area of this curve is negative. It's a triangle. 1/2 base times height is negative 2.5. So that brings us to 0. Yay. The slope starts at 0 and goes to a negative value. So you get a nice parabolic section. I know it's not to scale, but you get the idea. Now we go to the next section, which is negative. Now that's a trapezoid. I just happen to know the area of a trapezoid is you average the heights times the base. So the average of the heights would be 7.5 times the base is 1, so that'd be a total of negative 7.5. So 0 minus 7.5 brings me down here. And what's the shape? Well, the slope says it's the shear. The shear starts off at -5 and then gets even worse, right? -10. So I may not be able to draw this one exactly to scale, but you get the idea that it gets steeper. I can't really, I kind of missed the mark there, but you get the idea. Okay, now the change in moment from point C to D should be the area of the shear diagram, which is positive. Area of that is positive 7.5. That brings us back to 0. Great. Now you'll notice the slope is the same value, except instead of being negative, it goes positive, and then it ends up at a positive slope of 5, not 0. So you kind of get something that looks like that. So I guess if you were to look at it, this section of the curve is symmetric about the middle point, and then this section of the curve is symmetric about this point. So what's the maximum moment in the structure? Negative 7.5. So remember, sine is just direction. It's not associated with magnitude. So if you were worried about designing this beam and you wanted to have the maximum moment, you would want the fact that it was negative here. Now, if this is a reinforced concrete beam, what would you have to do? Well, in this segment where you have positive moment, you would have support in the bottom of the beam. In this section of the beam where it's negative moment, you'd have to have steel in the top. If you made it out of steel and you had a constant cross-section across the whole structure, you would worry about the maximum moment period. So see, it's different design strategies when you get into the materials, whether it's steel or reinforced concrete. But you'll worry about that next semester.
So the hinge does not break where you take the area from.
It didn't have to. It didn't have to. That's an interesting question. I could have computed my change in moment by going from here to here, and the area under this part of the curve, which would be negative 10 times 2, it's still 10. So 2.5 minus 10 gets you to 7.5. Okay. It still works. I just wanted to make sure that I actually hit 0 here, so that's why I stopped the area at that point, to make absolute sure that I had 0 moment at my hinge. Okay, any other questions?
Yeah, I got one.
Yes.
On three body diagram BCD, we have force By, which is equal to 5 kilonewton.
Right, it's acting down.
I mean By.
Oh, By, I'm sorry, By. Right.
On the second free body diagram.
Sorry, say again?
On the second free body diagram.
Yeah. Okay, so By, we came out with By as positive, so this is the right direction.
Yeah.
Okay, so this kind of force down is negative shear. So it came out to be -5. And a force up on the right side is also negative shear. So it's the same value. Remember your sign convention for shear, right?
Yeah.
I dropped my ruler. Hang on a second.
So I'll just remind you down here that if you had a little blob of material, that positive shear is down on the right and up on the left. This is positive shear. So you can see that on the left side it's negative, on the right side it's negative. So they're both the same. And it matches what we found. So the big issue here would be if you have to make some connections, the worst place to make a connection would be right over this support, because that's where the maximum shear occurs. The best place to make a connection is right there for shear, but it might be one of the worst places for bending. You have to keep that in mind. So a lot of people like to make connections where there's no moment. So this would be a great place for a connection. And that's why it may be a pin. Maybe that's a connected place where two elements, like two steel beams, are connected together with some plates. Right? So you just say, hey, I'm going to assume that's a hinge, because I don't think that has much moment capacity. Those are good questions. All right. We'll stop here.